All right. So we're looking at section 3.2. In 3.1, we talked about measures of central tendency. Um, and so those were looking at things like average, how the word average could refer to either the mean, median, or mode. Mean being what most people would think about what average is, add them all up, divide by how many there are. Median, the middle number, where half of the data, at least half the data is that number or less, and at least half the data is that number or more. Or mode, which value occurs most often. It's what we might, any of those we might refer to. Now, of those, the one that is probably going to be used most often is mean. We'll use mean most often there, but we'll refer to median also on occasion. And then variation, an attempt to describe the spread of the data is what we're going to look at today, and just how spread out is the data. And so if we were looking at a few data sets there, you might have something where you have a data set where you have some things down here and some things over there and then some things like that, and it might be very spread out. You might have a different data set where everything is kind of in the middle of the data set. So this would be like a high variation, where that's not working very well, where this is a low variation, right? Kind of everything's central. So it's kind of, when I was undergraduate going through science classes, one of the things they talked about was the difference between accuracy and precision. So if you think about, if you had a bullseye here and you had like a shot here and a shot here and a shot here and a shot here and a shot here, and then someone else had a shot here, a shot here, shot here, shot here, shot here, your shots are much more accurate, right? You're closer to the bullseye, but how spread out your shots are, is more than how spread out the other person's shot is. Their shots are more precise. And so if they could be, they're basically consistent. And so if you could like somehow adjust them, hey, stand a foot over here and aim lower, they might be much more likely once you do that adjustment to hit that bullseye. Whereas you need to work on moving your things closer together, be more precise. But that's kind of the idea. Variation is how spread out the data is between those. So let's see, can I delete that? So let's erase all that. That's what I want. Clear. All right. Sorry. Getting to know this thing. So one of the most basic ideas of variation, or how spread out the data, is the idea of range. Not to be confused with domain and range from algebra, though there is some relationship there. But so the range is what's the difference between your highest value and your lowest value. So you take your highest value, you subtract it from your lowest value. It just tell you, what's that distance between those two values. Between those, it's very, very basic idea of what range is. Now, of course, there might be issues with outliers and things that could make this range much larger than really you would expect, but that's the idea. Just figure out how far is it from one end to the other of your data set. So let's look at a set of data here, kind of review this stuff, find the mean, median, range, mode, and range of the data. And I kind of go in a different order when I do that. I like to do mode first because I think that's the easiest, especially if things are kind of sorted like these are. So 10 would be the mode. That's the number that occurs most often. So we have 2 10s versus one of everybody else. Median is the next, I think, kind of the easiest one. So we got 6 values here. So the median would be somewhere in there where you have 3 of the numbers below it, 3 of the numbers above it. And the way you figure that out in one of these cases is we find the midpoint between 10 and 30. So we're going to add 10 plus 30, divide by 2, so 40, divide by 2. So 20 is the median score. And you'll notice the median doesn't have to be part of the data set. Sometimes it is, but in this case it's not. So half of the numbers are below 20 and half the numbers are above 20. And then mean, this is where you usually do the most work. We're going to add all these up. So what do we got? 10, 20, 50, 100, 150 over 6. So I think that's what, 25? Let me verify that. 150 divided by 6. Yeah, 25 is our mean. And just kind of remember X bar, because this is a sample, we're assuming this would be the sample mean. If this was a population, the entire population, we would use Greek letter mu to represent that. And then the range. So this is that new idea. How spread out are the data? And the highest value is 50. The lowest value is 5. So the range is 45. So 45 units is how spread out from lowest to highest on there, or highest to lowest, however you want to think about it. So there's a 45 unit spread between those two. All right. So let's go to the next slide here. So let's talk about some symbols we're going to see. We're talking about variation. Sample variance, we're going to use S squared. Now you might be wondering, why are we putting square on there? Well, that's because sample standard deviation is just S, and there's a relationship between those two. If you were to square the standard deviation, you'd get the sample variance, or how is more accurate, when you take the square root of the variance, you get the sample standard deviation. We're going to see those calculations. For populations, population variance is going to be sigma. This is lowercase sigma squared. And then population standard deviation, we're going to use just sigma itself. And same idea. You take the square root of the variance and you get the standard deviation. And then lastly, we're going to look at the coefficient of variation. It's another thing we're going to look at here briefly. We're going to spend a lot of time on it, but talking about how to do that. All right. So what I would recommend you do is pause this video and then go watch the video. What is standard deviation for the rest to make sense? And then after you get done watching that, come back to this video. But we're just going to go on here. So I'll give you a second to pause it. All right, so I assume you came back, and let's move on. So variance. So variance is a measure of the squares of the differences between the individual values and the mean of the data set. And hopefully if you watched that video, you kind of had an idea about what we're talking about there, about how spread out is each value from the mean on average. And then the larger this value is, the greater the variation in values. Now, you want to be careful about that because it all depends on the numbers you're working with. When you're comparing variance between two similar data sets, then that makes sense. That can tell you something about that. But if they're completely different data sets, even though one is bigger than the other, you might be dealing with bigger numbers. So it may or may not make sense a whole lot to tell you, but in general, this is true. The larger the number, the more spread out, the more variation, the bigger the variance in those datas. All right, so here's a couple of formulas you can use. This first formula is the formula we're going to use. This is kind of the standard formula. Like I said, if you watch that video, you probably ran across that formula in the video or something close to it. I don't know if you had the n-1. I can't remember if you put the n-1 on the first one or not. But that's kind of the idea there. This is just another version of it. If you didn't want to use the mean, basically they're kind of figuring out something around, kind of working around doing the mean. But this first one is the standard one. That's what we're going to focus on. Okay, so let's say we have this data set and we want to find the variance. So I made a little chart here. You might want to organize your data in this kind of chart and try to use it to calculate it. That's up to you. Another thing you probably will want to know is what's n, and in this case, our sample size was 6. So n-1 is going to be 5. So notice that's in the formula. We're going to need to know that. So we already figured out the mean was 25. So we're going to take each value minus the mean. So we're going to take 5 minus 25 and get negative 20. 10 minus 25, negative 15. Again, this is also going to be negative 15. 30 minus 25 is positive 5. 45 minus 25 is positive 20. And then 50 minus 25 is positive 25. Now, if you have a sample data set like this, when you calculate these differences, I think on the video he discussed how if you add these up, this would always come out to be 0. So yeah, it looks like 50 and 50. So yeah, that would come out to be 0. So that's why you don't want to use those. You want to square those. And so we're going to square each of those. So 400, 15 squared is 225. Yeah, so 225. This is also 225. 25. That's also 400. And then 25 squared, 625? Yeah, 625. All right. So according to our formula, what we need to do is add all those up. We're going to take the sum of those. So add those together. Okay, so it looks like it comes out to be 1900. And so to figure out the variance, remember this is the variance, we're going to take 1900 and divide it by not our sample size, one less than our sample size. And so divide by 5, and that gives you 380. Okay. Now, what does that mean? Again, if I was comparing a similar data set and they got 420, I would say, oh, well, that other data set is more spread out than this data set. And if I got a similar data set and I got 210, I would say, oh, well, this one's more spread out than that one. Within the context of this particular problem, though, all by itself, that doesn't tell me a whole lot, which is part of the reason we don't use variance a lot by itself, because it doesn't really directly tell you a whole lot of stuff. Also, because you're squaring things, the units are squared. So, if these were all like feet, this would be square feet. Well, what does that tell me about the feet, though? The spread of the feet, when it's square feet. So there's that problem with variance as well. So which is part of the reason we don't use a lot of variance there. All right, so let's go on to the next slide. So what we use more often is standard deviation. And so standard deviation is another way of talking about the variation, how spread out the data is. But we're going to take the square root of the variance. And an advantage to this is, like I said in that before, if everything was in like feet, then this would also be in feet, not square feet. And so it would tell you something about the data itself directly. So all we're going to do is we're just going to take the square root of the variance. That's how you figure out the standard deviation. So in the case of a sample, we're going to look at the square root of the sample variance, and that would give us the sample standard deviation. But in the case of a population, you would take the square root of the population variance. Now, well, I guess I'll talk about this later. Let's move on. All right, so we figured out our variance was 380, which means our population standard deviation, or sorry, our sample standard deviation here is going to be, oh, is this going to work? Maybe it will. 380. I don't like that. Let me use the other tool I was using before. Okay, so square root of 3, and I guess this one's acting up as well. All right, is about, and we take that square root, and we get, I'm going to round that off to 19.5, 19.5, whatever, feet, meters, pounds, whatever. So remember our center of our well, I shouldn't say center, the mean of our group was 25. And what this is telling you is, on average, your numbers are about just a little shy of 20 units from there. So if you think about, like, if I went 19.5 up, I would just be a little bit shy of that one. If I went 19.5 units down, I would be just shy of a little bit of 5. And what I'd see is, like, half of my group is within, 3 out of the 6 is within 19.5 units one way or the other, with the other half being outside of that range. So on average, about half of them are within there and about half of them without there. On average, it comes out to be about that. And that is pretty typical there. So that's what that's telling you, that standard deviation. And that's something meaningful to know, how spread out is the data. It's like, well, it's the center's around 25, but about half of it is, a good portion of it is within about a little short of 20 units from there. And there's going to be more stuff we're going to be able to figure out from there. Using standard deviation is going to come in a lot more. All right, so up to this point, we've been pretty much talking about samples. So let's talk about a little bit about populations. To calculate the population mean, again, you use all the values in the population and you divide by the entire population size. That's what the capital N stands for. For population variance, remember for sample variance, the formula, we looked at this formula, N-1, the sample size -1. Whereas on this one, we're just using the population number. We're just using the population. And then to get this population standard deviation, again, you take the square root of the variance, population variance. Okay, so why is this an N instead of N-1, like that other one was an N-1? So what I would do is recommend you pause this video and you go watch the video for N versus N-1, and then come back. Now, I'll give you a minute to pause it and go do that. Okay, so I assume you come back. I'm just going to summarize that real quick in case you didn't quite get what was going on there. Basically, this formula right here, this population variance, is the true formula for variance. So if I wanted to find the variance of the sample, so if I wanted to find, here, if I want to find, oh, sorry, messed up. Let's go back to share. Okay, it's all messed up. What's going on here? Okay, push the wrong button. That was on me. So if I wanted to say, what is the variance of the sample? Okay, I would actually use this formula, right? I'll just use that, but I would actually use this formula if I wanted the variance of the sample. This is not the variance of the sample, and it's going to seem like I'm playing with words, but I'm not. This is actually the sample variance, which is different than the variance of the sample. So the sample variance is an estimator. This is supposed to give you an estimate for the population variance of the true population. Here, let me go in here. I'm going to erase that. I don't know what I want to call that. I don't want to call it. I want to call it S squared, but maybe I'll say, come on now. Okay. Maybe I'll say S squared. I don't know. I'll just say X or something. So I don't know. It's different than the sample variance. Okay, so this is the actual, if I use this formula at the bottom here, this would actually be the true variance of the sample, true spread out. But the sample variance isn't supposed to do that. It's not actually supposed to give you the true variance of the actual sample. What it does is it gives you an estimator for the population variance. So it's a little off from the sample itself. It's basically like saying the sample isn't a true measurement of the actual spread of the original data. And so we do a little adjustment, and that adjustment is this N-1. And so to say, okay, if you did this true calculation, you'd be too small. And the N-1 makes it a little bit bigger so that it gives you a better estimate of the actual population variance. that you're drawing the sample from. Okay, so I don't know if that made anything kind of clearer or not. Maybe it just made everything more cluttered in your head, but there's a difference between the variance of the sample versus the sample variance. The sample variance is an estimator for the population variance, not a true measure of the sample itself. It's trying to say, okay, this is going to tell you something about the population. So that's why it is. And if you go back and watch that video again, maybe that might make it a little clearer. I don't know. But hopefully it does. Hopefully it does. All right. So where are we at? Okay, we did this. All right. So real quick about the coefficient of variation here. It's just kind of telling you in relative scale how the standard deviation compares to the population mean. You know, is it much smaller than the population mean? Is it bigger than the population mean? Maybe if you have some positive and negative numbers, this actually could come out to be bigger. But just in relative scale, what is it is, and it's measured as a percentage. Measured as a percentage. So here we have again variation, standard deviation of our little sample here. We probably also want to know that our mean was 25. And so it's asking us, what's the coefficient of variation? And so what we would do is we would take our 19.5, our standard deviation, and divide it by the size of our mean, and then multiply that by 100%. And we would get, what is that, 19.5 divided by 25 times 100%. It's about 78%. Okay, so 78% of the standard deviation, or sorry, of the mean is covered by the standard deviation. So if you go from the mean down 78% of the way, you're going to hit a standard deviation. And then also if you go about 78% of the size of the mean up, you're going to hit a standard deviation that way. Kind of telling you how that's spread out. So it's just a measure of the relative sizes of those there. So like I said, we're not going to spend a lot of time on that, but just it's something sometime that will come up. All right. Chebyshev's theorem. And Chebyshev's theorem, what it tells you is it tells you about what portion, what basically percent, though as a decimal, of the data falls within a certain number of standard deviations of the mean, given by this formula, this 1 minus 1 over k squared. So if you say, about how much, or at least how much, let me say it that way, at least how much of the population of data in the sample should have fallen, or population, if you have the population standard deviation, within 2.5 standard deviations above and below. Again, it's above and below. It's in both directions. That's how this formula works. So now there is some restrictions on here. This formula doesn't work if k is negative, because you only talk about standard deviation. It doesn't matter which direction you go. We're just going to say, okay, it's this number of standard deviations. Also, it's got to be bigger than 1. So it doesn't work for any number of standard deviations, 1 or smaller. So it's always got to be bigger than 1. So we're looking at, 1.1 standard deviation, it would work. 2 standard deviations, 5 standard deviations, 11 standard deviations, however many, as long as the number is bigger than 1. As long as the number is bigger than 1. Now, what's interesting about this formula is it doesn't matter about the distribution. No matter what kind of distribution, it doesn't matter how spread out. You could have a distribution that looks like I don't know, something like a bunch of numbers this way, and then very few in the middle, and then a bunch of numbers out to the edges, and this formula is still going to work. It's still going to work when you know where the mean is, wherever that mean is, and you know the standard deviations from that mean. This formula is still going to work regardless of how this data is spread out, whether it's mound shaped, whether it's like something inverse mound shaped, like something like this, or maybe bimodal. You might think this is bimodal, or skewed left or skewed right. Uniform distribution. It works for all of them. It works for all of them. Now, later in the semester, we'll talk about mound shaped and how there's a stronger amount, just as long as we know it's mound shape. But if we don't have any idea what the distribution is, all we know is the mean and the standard deviation, we can use this to say, well, at least how this portion is within sorry, not one. It'd be bigger than one. Within 1.5 standard deviations or 2 standard deviations or 10 standard deviations or whatever. We can be certain of that no matter the distribution. No matter the distribution. So that's an awesome thing about this Chebyshev's theorem. So let's do some calculations, some basic ones. All right, so let's look at what if how much is within 2 standard deviations, how much is within 3 standard deviations, how much is within 4 standard deviations. So again, that formula is 1 minus 1 over k squared. So remember, these are the number of standard deviations we're looking at here. That's what k represents. So 1 minus 1 over 2 squared. Well, 2 squared is 4. So 1 minus 1/4 is 3/4. So 0.75, or 75% of any kind of distribution. 75% of that group is within 2 standard deviations. Always. Might be more, but it can't be less than 75%. It will always be, and you think about, well, what if it's way spread out? Well, that just means the standard deviation is going to be bigger. And so then you're going to cover it within 2 standard deviations. What about 3 standard deviations? So again, we put 3 into our formula here. 1 minus 1/9, that's going to be 8/9. 8/9 is about 8 divided by 9, 0.889. So 88.9% of any kind of spread is always within 3 standard deviations, above and below, contained within that. And then 4 standard deviations, 1 minus 1 over 4 squared. So 1 minus 1 over 16 is 15/16. 15/16 is about, let's say 0.9375. So about 93.75% is within 4 standard deviations of any kind of thing. And again, like I said, when we look at where we just restrict ourselves to mound shapes, these numbers are much higher. These numbers are much higher. But any distribution, 93.75% is within that. So if someone says, well, you don't know how spread out or what the shape is of the data, you can always say, well, it doesn't matter. I know within 4 standard deviations, there's going to be 93.75% of the group within that. So that's always true. So that's an amazing thing about this formula. Okay, so let's do a little bit of algebra. So let's say I want to know, you tell me, I want to be a certain percentage. Let's say 80%. I want to know how many standard deviations do I have to go out from the mean to get 80% of the data, guaranteed. That I'll get at least 80%. And so what we're going to do is we're going to do a little algebra here and move stuff around and solve for k. I'm going to get that k so I can know what standard deviation. Now, just realize, again, k is a number of standard deviations, and p is a proportion, but as a decimal. So if you're saying 80%, you'd say 0.80. So, but let's do some algebra first, and then we'll figure that out. So one thing you can do when you're looking at something like this is you could actually, I guess, let me turn this on. You can actually flip-flop these two. Basically subtract p to that side and add 1 over k squared to this side. So that would give you 1 over k squared equals 1 minus p. Let's get rid of the fraction. Multiply both sides by the denominator. So multiply both sides by k squared. So this is 1 equals 1 minus p times k squared. We're trying to solve for k. So we're trying to get k by, so let's get rid of this parenthesis. So let's divide both sides by 1 over p. 1 minus p. So k squared equals 1 over 1 minus p. Get rid of the square by square rooting. Normally it'd be plus or minus, but again, we're just talking about standard deviations. And we said for this formula to work, k has to be a positive number. So we're just going to worry about the positive square root of 1 over 1 minus p. All right. So there is a formula. Now, if you get a number less than 1, then you would know, or 1 or less, it doesn't really make sense. It shouldn't happen, but it wouldn't make sense. All right. So let's say I want to know how many standard deviations to get 80% in there. So I'm going to go to this formula and I'm going to put in 1 minus 0.80 in there because that's 80% as a decimal. So square root of 1 over 0.2 or 0.20, what is that about? So 1 divided by 0.2 square root. Looks like I need 2.2, let's say 4, 2.24 standard deviations from the mean to guarantee I'll get 80%. Depending on the distribution, I might not need that many, but any distribution, if I go out 2.24 standard deviations, I will guarantee I'll get 80%. And if we go back and look, 2.24, so let me clear that out and go back. Oh, I erased it. Yeah, and so it should fall between the 2 and the 3. So that's kind of interesting. All right, so let's look at this problem. After taking a random sample, it was found at a college that the average age of students was 20.6. So that's our average. That, you know what? I don't know why I said that. See, this is why you're always learning. You're always learning. I shouldn't say average. The mean. This is what this should be. The mean age. The mean age of the students was 20.6. I'm just in everyday parlance, people are going to mix the two up. It was 20.6, and the standard deviation was 1.25 years. At least what percent of students are 19 to 22.5? So we have no idea what this distribution may look like. We don't know if it's mound-shaped, bimodal, whatever, you know. So let's figure this out. So 20.6, that's our mean, okay? And then 22.2 and 19 is what we're trying to figure out what percentage falls in there. So how far is it from there to there? How far is it from there to there? And it looks like it's about 1.6 years that way and 1.6 years that way. Great, they're the same. Thankfully, thankfully that. Now, how many standard deviations is that? Well, to figure that out, you take how big the gap is divided by the sample or the standard deviation size. And that will tell you how many standard deviations go into 1.6 or how many standard deviation 1.6 is. So 1.6 divided by 1.25 gives us 1.28 standard deviations. This is our K value. This is our K value. This is a number. This is the number of standard deviations from the mean we went both ways. And so at least how many, again, we don't know anything about the distribution, so we can do the Chebyshev's theorem. 1 minus 1 over K squared. So now we know how many standard deviations we went each way, right? Standard deviation. I probably shouldn't change notation, right? So let's say this is still a sample. So sample standard deviation 1.28 that way and 1.28 that way. So I put that in my formula, 1 minus 1 over 1.28 squared. Figure that out. This should be less than 1. If you're not getting less than 1, you might check your math. 1.28 squared. Okay. Looks like 0.39 or about 39% are within that span. Guaranteed. Now it's probably more, but if we knew it was mound shape, we'd probably be very sure it's more, but we don't know that. We don't know that. Just double check that. Yep. So about 39%, at least that number, are within 1.28 standard deviations, or in other words, are between 19 and 22.2 years of age. All right. Let's go on. All right, so here's a problem. I can't remember exactly what the problem was in the book. This is an older version of the book, but I think it had to do with they went to a small village that they're worried had people dying off at a young age. And so they're trying to figure out what the relative age is of the thing. And what this deals with is how do I handle it when I don't have a bunch of values, but instead I have individual classes and frequencies of the classes. How would I do this calculation in that case? And so we're going to do an example in that case. And the formula is a little bit different, but it's the same general idea. So since we don't know the actual ages of everybody within the different classes, what we do is we take the midpoint value of the class. And the way you calculate the midpoint is you add the bottom value of the class to the top value and then divide by 2. So 1 plus 10 is 11, and then divide by 2. So 11 divided by 2 is 5.5. 11 divided by 2 is 5.5. So this is 5.5. And then you could do the same thing. 11 plus 20, 31, divided by 2 is 15.5. But if you remember like class width, when we calculate class width, it's the same no matter what value, as long as you're jumping from spot to spot. So looking at this as a class width of 10, you add 10 every time. So if I add 10, 25.5, add 10, 35.5. Now, in this particular problem, they said to consider everyone 31 and over to have an average age of 35.5. Is that a good estimate? Probably not, but that's what they just to do the problem. They made that kind of idea. All right, so then we're going to do the frequency of every class. So this has a frequency of 34, this has a frequency of 18, 17, and 11. The entire frequency, I believe, was 80, if I remember right. Let me get to that problem. Oh yeah, this has a bunch of computations we're going to do. Okay, so 80. All right, so what we're going to do is we're going to multiply each of these. Well, just a reminder of how you find. Well, we need to find the mean, right? And so for weighted mean, what you do is you take the value, in this case, the midpoint value, times the frequency. And then we're going to divide that by the sample size. So that's why I'm calculating the value, the midpoint value times the frequency here. So I'm going to take 5.5 times 34, and that should give me 187. I'm going to take 15.5 times 18, and that should give me 279. 25.5 times 17, that should give me 433.5. 35.5 times 11, and that should give me 390.5. And if I add all that up, it should come out to be 1290. Okay, so I'm going to take 1290 divide by 80, and that's going to give me 16.125. Right? Okay, and just kind of, again, remembering what we're really saying here is, think about if there was a list of 80 values. 34 of those values we're going to say are 5.5s. 18 of those values are 15.5s. 17 of those values are 25.5s, and 11 of those values are 35.5s. That's basically what we're doing. That's what this whole multiply by the frequency, the value times the frequency. It's like if there are 34 5.5s, you don't have to say 5.5 plus 5.5 plus, for all 34, you can just say, well, if I know there's 34 of them, just multiply 34 times 5.5, and that's the sum of that entire portion. So that's what's going on here. Okay, so now that we know what the mean is, we're going to take each of these midpoint values minus the mean value. So if I take 5.5 minus 16.125, that's going to give me negative 10.625. If I take 15.5 minus that, that's going to give me negative 0.625. If I take 25.5 minus 16.125, that's going to give me 9.375. If I take 35.5 minus that, it's going to give me 19.375. Now, one thing I want to point out, this kind of threw me off when I first I had to think about it for a second. And oh, of course, if you add these up, you're not going to get 0. And that's because we're not going to every value and subtracting it, right? When we did this, we didn't take into account the frequencies. So if you were to multiply 34 times negative 10.625, 18 times negative 6.25, 17 times that, 11 times that, and then added those answers up, it would come out to be 0. But since we're not taking in the frequency, it's not going to add up to be 0. So I just don't want people to get thrown off by that. This isn't going to add up to be 0. All right, so we're going to square each of those. I'm going to do a little bit more rounding as we go forward here. 112.9 is what this rounds off to be. This rounds off to be 0.4. This one 87.9 and 375.4. Okay, and if I remember right, this was like 8939, 8939, so very close to those values. So that's why I rounded, just kind of make the numbers a little bit more manageable. And then what we're going to do, so here we go. We're going to figure out the standard deviation, or sorry, not the standard, the variance. We're going to find the variance. So the formula is a little bit different than what we looked at before. What you're going to do is you're going to take the midpoint minus the mean times the frequency, and we're going to add all those up. And then we're going to divide by n minus 1. Again, we're doing samples. So sample variance, you always divide by 1 less than the sample size, not the sample size, because we have to push it up to estimate for the population. This is supposed to be a population estimate. All right, so square or take each one of these times the frequency. So we're going to multiply it by the frequency this time. So multiply that times that. 34 times that 112.9 gives us 38.6. 18 times 0.4 gives us 7.2. Multiplying the next one, 1494.3. Multiplying the next one, 4129.4. Okay, and so that's the difference of the midpoint from the mean squared times the frequencies, and then we're going to add all those up, and those add up to be 9,469.5. Okay, 9,469.5 divided by not 80 this time, but 79. Remember, n minus 1. And that comes out to a variance of 119.87 years squared. So again, within the context of the problem, it doesn't really mean a whole lot, which is why we don't use variance directly a lot. Instead, we would say, oh, the standard deviation is about 10.95 years. And what that means is about, on average, an individual is going to be within just short of 11 years of 16.125 years, right? So, you're expecting on average people are somewhere between like 6 years old and 26 years old in this group, which is a pretty young population to look at there. Now, that may just be a young population, or maybe something's going on and people life expectancy isn't reaching, and that might be something for concern, which is why you might do a study like this. Okay, so that is the information for this section. Be sure to do the assignment, problems 1, 5, 11, 15, 16, and 23. Have a good day there, and I'll see you later.